In past labs, we've used Newton's second law to describe and model the movements of objects we can see. In this lab, however, we will use the same scientific principle to find out qualities of objects we can't see based on the interactions between visible objects and the unknown objects which we predict must exist due to the nature of the observed movements. For this lab, a so-called black hole was imagined to be the source of the forces acting on our known object. The known object was observed once daily for an entire year. Its x and y coordinates for each time t were then compiled into a spreadsheet. Using this given data, the velocity of the star during each time step could be estimated using the formula v equals the change in position over the change in time. The program VPython was then used to iteratively calculate a velocity for each time step. Then each of these velocities was used to approximate the net force acting on the planet at each observed position. Because we don't have any information about other large objects in the vicinity of the black hole and the star, we assume that the gravitational force of the black hole is the only significant force acting on the star. And using Newton's universal law of gravitation, we were able to estimate the mass of the black hole to be 3.566 times 10 to the 31st kilograms. Besides approximating the mass of the black hole, another important component of this lab was modeling and understanding the behavior of the vectors Fnet perpendicular, Fnet parallel, and their sum, Fnet. We know from Newton's second law that Fnet equals dp over dt, but it's worth noting that for this experiment we have approximated Fnet and its parallel and perpendicular components to be delta p over delta t, where delta t equals 86,400 seconds, or 1 day. If one were to observe the position of the star for smaller and smaller time steps delta t, one would essentially manually, or with a computer approximation, be taking the limit as delta t goes to 0, approximating dp over dt. However, in this case, we've decided, based on the data available, that 86,400 seconds per time step is sufficiently small to understand the movement of the star, model the forces acting on it, and approximate the mass of the black hole. Using an excessively large number of data points in a computational model such as the one we have here can also lead to truncation errors, which actually reduce the accuracy of the computed data. We now have established the fundamental laws and basic plan for how to model these interactions. The next step is to write a code in VPython which will iteratively calculate the velocity, momentum, and parallel and perpendicular net forces for each time step delta t. We can also use these various values to calculate the mass of the black hole. Setting up the VPython code. The mass of the star and the position of the black hole were inputted. I also created a sphere at the position where the black hole would be. Although we can't actually see it, I thought it'd be useful to have some kind of frame of reference. The universal gravitational constant was also specified here. Delta t, the time step between each set of data points, was also specified. And here's the while loop that calculates the velocity for each time t by finding the change in position over the change in time. Using another loop which defines the initial velocity and final velocities to be those pertaining to the two sequential points, we can calculate a delta v and delta p for each day. We now have delta p and delta t for each section of the star's movement, so we can calculate Fnet using Newton's second law. Fnet's parallel component can be calculated using the mag function in Python, and its perpendicular component is the difference of Fnet and Fnet parallel. We then calculate the value of r, the vector which points from the star to the black hole. Again, using the mag function, we can find its magnitude. We take the magnitude of Fnet and finally move to calculate the mass of the black hole using Newton's universal law of gravitation. It is only at this line that we assume that Fnet, or the magnitude of Fnet, equals the magnitude of the gravitational effect of the black hole on the star. If the star were indeed being acted on by another force, this line would be wrong. I could have defined Fgrav and set it equal to Fnet, but for the sake of brevity, I merely substituted Fnet here. Now to run the code. As you can see, the yellow arrow, which represents Fnet, always points toward the black hole, because we've said that is the only force acting on it. The black arrow, the parallel component of Fnet, points in the direction of travel until just after the star passes the black hole. Then it switches orientation, indicating that the star went from speeding up to slowing down. The blue arrow, Fnet perpendicular, points toward the center of the oscillatory circle. Finally, we see the calculated mass of the black hole for the final time step here, a value of 3.56622 times 10 to the 31st kilograms. If another black hole were placed in the same location and the motion of the star remained unchanged, it is impossible for the mass of the new black hole to be different than that found here. The movement of the star depends on the value of Fnet, and according to the assumptions made here and Newton's law of universal gravitation, our Fnet is directly proportional to the mass of the black hole. If the observed movement is the same, the mass must also be the same. A problem I see with this lab. While the black hole is 10 times as large as the star, I think it likely that the black hole would experience some kind of effects of gravitational force of the star. This lab did not account for that. The position of the black hole was set. Thanks for watching.